Hey, welcome back. So in this video, I thought we'd spend a little bit of time on the DeepSeek R1 zero model. And in particular, we're going to look at reward modeling, which is this key fundamental piece of reinforcement learning. It's this idea of whenever a model gets something right, you give it a reward. And whenever it gets something wrong, it doesn't get a reward. Now, in this video, we're not going to look at the reinforcement learning part, but we are going to specifically focus on the reward modeling rule verification system that DeepSeek used when training their model, and then how you can do the same when you're building your own models yourself. And in particular, we're also going to look at the same method that DeepSeek used to be able to evoke good chain of thoughts that could then be used to verify the model. So as I said before, if we look at the DeepSeek paper for a second, in table 1, you can see this piece here where they have a prompt template that is used to evoke good outputs in the format they want for the model. So you see here a conversation between user and assistant. The user asks a question and the assistant solves it. The assistant first thinks about the reasoning process in mind, then provides the user with the answer. The reasoning process and an answer enclosed within think tags and answer tags respectively, i.e. think reason process here and answer here. And then essentially the question, the prompt that you're going to ask, tell me a joke about cheese, what's 5 plus 5? That goes in this prompt piece. And then after the assistant, then it's going to evoke the model outputs. Now, once the model has evoked the outputs, and again, we'll deep dive into how that looks and how that gets sampled a little bit later on. But once that's outputted, then there's this thing here called reward modeling. And this is the fundamental part of reinforcement learning, where essentially the reward is the source of the training signal, which decides the optimization direction of RL. So in this case, they are using a rule-based reward system that consists of two types of rewards. One is accuracy rewards, so it evaluates whether the response is correct. So if I say, what's 25 plus 2, then the answer is going to be 27. So basically, the model needs to give an output that says 27. If it doesn't, it gets it wrong and it doesn't get its reward. And then that also doesn't just work for things like math problems. It works for code as well, because you can use compilers, you can run unit tests to be able to say whether the code that generated came back with the right answer. And then the second part of this is format rewards, which is in addition to the accuracy reward, they have a format reward model that enforces the model to put its thinking process between think and think tags. Now, the interesting thing about this is they're just focusing on a rule-based reward system. They're not doing things like process rewards, etc. It is literally just checking for whether the model came back with something that was accurate and whether it came back in the right format. Now, in a future video, we're going to go into GRPO and we'll look at how reinforcement learning works. But in this video, we're just going to focus on the reward modeling exercise, how to create your own verifiers and how to get the model to evoke those responses. And then we will see actually how it looks and how accurate it is. So in order to do that, we are going to call one of the verifiers I pre-built. This actually simulates what the format reward verifier for DeepSeek actually is. And in this case, you see I've given it a URL. You can actually go and try this yourself. I hosted it, but the code is also up in my GitHub, so you can run it locally as well. So we are just going to call this URL, which is my verifier URL. And then I'm going to pass in the text from the model. Now, I'll show you how to evoke that text a little bit later on. So you see here, text is think. The sum of 3 and 4 is calculated by the adding two numbers together. 3 plus 4 equals 7. So this is the two think tags, and then I put my reasoning in between, and then the answer is 7. So really, as long as I've got a think and an answer tag, it doesn't matter what's in there. It could say, I like cheese. As long as it does that, it's going to come back with an answer. So if we run that for a second, you can see it comes back with score is 1.0. Now, if I change this, and rather than having think, and if I just write something like thonk, you can see the score is 0, feedback is null, and that is because there is no think tag. So if I put this back to think, and then maybe I change my answer. So rather than put an answer, I put ANSI. You see, again, a score of 0. Okay, so if I put that back to think and answer as normal, you can see the score comes back as it did before. Now, what I am going to do here is I'm going to change the answer. As I said, this is only checking that the format is correct. So if this time I say 70, you can see the score is going to come back as 1 because it doesn't care what the answer is. It only cares that you've got the think and the answer tags as specified. And this, as you can kind of see here, this is exactly exactly as the format reward is. So as it says here, in addition to accuracy reward model, we apply a format reward model that enforces the model to put its thinking process between think and think tags. So as long as I can get the model to generate out good text, i.e. the think and the answer, then I can come back and say, yes, you got this correct, or no, you didn't. Now, what is probably a little bit different about my verifier here is I also have this thing called feedback. Now, in the case of the DeepSeek modeling, they are not providing any feedback whatsoever. But I think that this feedback concept would be useful in the future. So if I just set that to true for a second, you can see I get feedback. Text correctly includes both think and answer tags within valid content. And again, if I change this from think to thunk again, and then we run that, you see text doesn't conform to required format, ensure it follows think, reasoning, blah, 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 blah. So it's quite a useful thing having this feedback thing, but it's not actually used in the training today. But I think we could probably change that in a future video. The only thing it really cares about is that score there. So I get 1.0 if it gets it correct, and I get nothing if it gets it wrong. And this is rewards, right? This is the key thing about rewards. So when we get into reinforcement learning in GRPO in a future video, then this score is actually what is used to improve the training. So every time it gets it right, it gets that score of 1, and therefore the model does a little bit better, it gets its reward, and then it's going to modify its future outputs to continue to get those rewards. If it gets a 0, then it knows it's got it wrong, and then it needs to do something 0, and then it'll edge towards where it got it right before in the past. So as I said before, this is in my GitHub, so you can go and download it, you can mess around with it, and all the instructions are there. The key thing that you probably want to understand is that in this kind of verifiers reasoning folder, the one that we were looking at there is a thing called reasoning format verifier. So this is it here. It inherits a base verifier that I created, but you can see it's just doing a simple regex, so it's just looking for the think and answer tags there, and then if it comes back, if it gets that right, if the regex passes, it gets a score of 1, and otherwise it gets a 0. And then the key thing here is in this verify with feedback, you see that if the regex doesn't match, it gets a little bit of feedback there, ensure it follows the think reasoning tags there, and then it's also checking for things like empty answers, etc. So that is how the whole mechanism works. Super simple, but what's really cool about this is you can extend this. You can, it doesn't need to be restricted to this reasoning format verifier. You can go and add your own verifiers as well. So let me show you how that works for a second. So let me show you what I mean, and we will actually do another verifier. So in this case, I want to extend this. I want to be able to distinguish between the answer that is being used for verification purposes and the answer that is used for the human. So you can see here, I'm going to stick with this think, but now I'm going to introduce a tag that is called verifier answer as well as the answer tag. So I'm going to need 3 tags. And basically, I'm going to use whatever's in the verify answer tag to be able to verify that the answer is correct, i.e. the accuracy reward. But the answer one is what the human would see. And that's really important because a verify our answer can be a really automatable answer. So if I say 25 plus 2, then the answer there should be 27, and that should be in the verifier answer is 27. But in the answer tag, I made something like the answer to the sum is 27. Why that is important? Because in the answer tag piece, then that's really hard to verify that from a rule-based system. But within verifier tags, because it's clean, it doesn't have all that preamble, then it'd be able to come back with the right answer. So you can see here, if I run this one here, it's a different verifier, and this time I'm going to call reasoning format with verifier answer. And you can see there, score 1.0, strip match, it's got think answer verifier. And again, if I change any of the values there, so verifier answer is not provided, then it's going to come back with a kind of failure. So again, if I just remove the swear part, you can see it doesn't strictly match because I've changed the tag there. So it works in exactly the same way. And the only thing that I have done different is, you see, as I've used a different verifier name time, which is reasoning format with verifier answer. So this is what I'm going to use to do the accuracy rewards. It's slightly different from what DeepSeek does. So you can see here the accuracy reward model evaluates the response is correct. For example, in the case of math problems with deterministic results, they're going to ask to provide a final answer in a specified format within a box and enabling reliable rule verification of correctness. I'm going to use a verification answer tag, but what they want to do is use a latex box. Again, I can show you, it's really easy to be able to do that. So in this case, if I use a different type of verifier, so in this case, I'm going to use a verifier that I call is boxed answer, which is exactly what you saw in that paper there. So if we look at this for a second, you see text in this case is going to be the answer to the question. So if my question was, what's 2 plus 2, then it could have some preamble like the answer to this question is, but finally, it's going to have this box thing, which is 4. So 2 plus 2 is equal to 4. And then in the verifier here, we're going to pass through an argument, which is the gold solution, and we're going to be expecting boxed 4. So in this case, the model has to generate something that's going to say box 4, and we're going to expect something that says box 4 as well. So if the model generate the answer, what's 2 plus 2, and it said box 7, then it's expecting box 4, and it's going to come back and say this is the wrong answer. So let's run that for a second. And as you can see, feedback matches exactly models expecting 4, and the gold answer is 4 as well. So if I change this and we change that to a 7 here, you can see it differs. You know, the model was the gold answer was 7, but the model generated a 4 in that case. And then that is effectively, as I said here, what the accuracy reward is. So in this case, if I was then running reinforcement learning on this, I would be having 2 rewards on this case. I would have the format reward and the accuracy reward. And therefore, they would average out. And you know, basically, if it got 1 correct, then it would only get a reward of 0.5. And if it got 2 correct, it would get a reward of 1. And that is basically how DeepSeek has done this. And it's completely rule-based. There's no LLMs involved in that. And that is verifiers. Now, it's really cool, as you can imagine here, because this technique could be extended to absolutely anything. You could use this for code. So you could run unit tests. You could have one that does compilation. Basically, all you need to do is just keep extending your verifiers. In my case, as I said, I didn't really like this box solution because it meant that you always had to have the same output in this sort of box format, and it affects how the user is going to see this. So I wanted a way of being able to verify this without necessarily affecting what the user sees. And that's why I introduced these verifier tags. So in this case, if I'm doing a sum like what's 2 plus 2, then in the text bit here, I can say, here is my final solution. And then verifier answer is going to be 4 in this case. And then, as you see, I'm going to feedback, and then the gold solution here is going to be 4 as well. Now, obviously, this would fail the think format reward there, but this particular verifier is only checking for the presence of the verifier answer tags within this. So if I run that for a second, you see it's going to come back and say, matches exactly. The model generated 4 and the gold answer was 4. So it works in the same way as this box thing. But in this case, what I'm doing is putting things in between the verifier answer tag. And again, if I change the gold solution to 7, you can see that it differs. The model generated 4, but the gold answer was 7. And that is basically why I'm using the verifier answer tag. But I mean, apart from that, everything else kind of remains the same. So now we have the ability to verify our answers through the use of this verifier answer tag. We could do it with the box solution, but we also can verify the formats. And this is the kind of verifier framework. As I said, really powerful. You can use this for code. Anything that you can employ a rule, this will work. In fact, you can even do it for things like limericks. So for example here, if I run this verifier here, I created a verifier called a limerick verifier. And then in this case, the limerick will be, there once was a fellow named Lee. He was stung on the arm by a bee. He jumped with the start, then soon had and ended up free. So if I just run that for a second here, again, the feedback is going to be huge. I'll come back into that in a second, but you see the score here is 1.0. And what this limerick is doing, it is, in the feedback, is doing a line count check. So it's expecting 5 lines in a limerick. It's checking the A and B, so the A rhyme check. So a limerick, line 1, line 2, and line 5 need to rhyme. So you can see here that line 1, 2, and 5 rhyme. And then the B rhyme, which is lines 3 and 4, also need to rhyme. And then it's expecting a certain amount of syllables, so it's doing checks on all of that, blah, blah, blah. And then you're doing things like phonetics to make sure this works. Very kind of cool and complicated, but ultimately we're checking for rhyming. So if I just run this one more time, but maybe rather than saying there once was a fellow named Lee, maybe if I change that to Fred, for example, and then you can see the score in this case is 0.75. So it's got some rewards, but it's not fully got rewards in this case. And the reason is, as you can see, the Fred bit was wrong, but lines 4 and 5 did rhyme, and 2 and 3 did rhyme. So again, this is the key to being able to create reinforcement learning system, is being able to effectively reward model. What is cool about this is you don't need to use a large language model. If something can be represented as a rule base, then you're going to be able to create a verifier. But STEM type stuff like math, code, etc., anything that is scientific in nature or can follow rule base is going to work kind of naturally. But again, we've got other ones that do things like haikus, tankas, whatever. And again, the most important thing is, from a model perspective, it doesn't necessarily need to have answers given up front. It can generate whatever it wants, but as soon as it generates the right thing, then it's going to get the reward for getting the answer right. So in this case, it got 0.75, and then it's going to aim to get a better reward each time. Now, if you want to, you can even use an LLM to actually be a verifier as well. DeepSeek kept away from that in their paper. They wanted to stick to rule-based verification, and I sort of understand that. Because then if the LLM's got something wrong, then basically you're going to get wrong answers coming into your model as well. But you know what? You can do it. So in this case, I've created a verifier called an answer satisfaction verifier. So you can see here within the answer tag, I go, yawn, it is 4, right? And then the arguments I'm asking here is question is what's 2 plus 2, and then the gold answer is 4. So what this verifier is going to do is it's going to take the question, put that into the large language model. It's going to know that the answer is 4. If it gets the answer right, but it's not in a great format, then it's going to come back with some feedback. So if we just run that for a second, then you can see that it's going to execute there, but it's got a score of 0.9. The answer is correct, but lacks clarity in answer. And again, if I run it again, you see, and this is the problem with LLMs. I've ran the same query twice there, but you see in one case I got a score of 0.9, and then in another case I got a 0.6. So again, this is something you can use an LLM to be able to do this, but you may get varying results in that sense, and you would need to spend a bunch of time using LLMs to do that. But I did provide an answer satisfaction verifier to be able to do this if you want to be able to get that kind of vibe or preference to that. But I think you would need to spend a little bit longer doing that. So from DeepSeek wise, I sort of stuck with the kind of rule base, but you can do it. Okay, so we now understand what a verifier is. As I said, I've created a whole framework. You can go and build upon that, create your own verifiers, do whatever you want. And it's totally extendable. So again, go have some fun with that. This is one of the big things I would like to see in the future, is this community of verifiers, and have that as an open source thing where we can all pull and use the verifiers to go and train models kind of together. But we're going to move on from that. And what we're now going to do is try and get the outputs that we want in the format that we want from the model. And I'm going to use the exact same techniques that DeepSeek used in the paper. So, and the basic way that they did this is through essentially just querying the model with this prompt template and then getting an answer. So I'm going to use a little CLI that I created. This is in my Chuck fine-tune kind of code base. So if you see here, We've got chuck-fine-tune. That is up in my GitHub. You can just go and use that, and it's within the source CLI, and then within inference, it's within there. So it again, everything's on my GitHub. You can just use that. There's instructions on there. What's cool about this is you can change the device. You can put the device's CPU. You can put it as CUDA. You can put it as MPS if you're on an Apple Silicon, or you can even run it as MLX as well there. So I'm just going to put CPU for a second. I'm going to use the Qwen 253B base model. I am not using the DeepSeek model. I am not using any instruct models. I'm just using a tiny 3 billion parameter model here. And again, I can just interact with this. The reason I'm choosing a tiny model is just so it works on on regular machines there. So if I just type in hi here, for example, I'm in chat mode. You can see it's going to come back and say, hi there, how can I assist you, blah, blah, blah. And I'll say something like, tell me the time. And then it's going to say, nope, I can't do that because I'm a large language model, blah, blah, blah. And there you go. As I said, standard sort of chat model. Now, what we are going to do is we're going to do exactly what DeepSeek did here. And we are going to pass this prompt template in a conversation between user and assistant, blah, 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 as I explained before. And we're going to use that to evoke the outputs from the model. So in this case, I'm going to pass through the Qwen 253B model again. I'm going to set max tokens to 256. As I said, you can change the device here. So I'm just going to pass in MLX as my device because I'm running Apple Silicon. And then I'm going to put through that exact template that you saw before there. A conversation between a user and assistant, blah, blah, blah. Think here, answer here, and then here I'm just putting user, and then I'm going to put what's 10 plus 10, and then I'm going to put that assistant piece here. So I'm just going to run that for a second. It's going to use MLX, and then it's going to come back with an answer. You see the reason why I'm using MLX, it comes back a little bit quicker. But the key thing here is you can see it is generated out. It's got all of this nonsense, so it's generated all my prompt again. We'll come back to that in a second. But then once it's generated the prompt, you see it's came back with 10 plus 10 equals 20, answer is 20. So there's a few things to notice here. The first one is it's repeated that prompt, but the other thing is notice it's not generated the think tags, right? So that's probably one of the problematic areas with that is it's not guaranteed to generate the think tag. So one of the things I like to do just to sort of move the model along a bit is after the assistant is just sort of put in the beginning think tag here so that the model then is sort of prompted into generating the reasoning. So in this case, I'm just putting think there, but then after that, you can see there, it then completes it out. So 10 plus 10 is the same as 10 plus 10 equals 20, think, and the answer is 20. This is a terrible chain of thought, but it is generating the thinking and the reasoning, right? As I said, this is the exact same prompt, except I'm just adding in the think there. In their paper, they ended up doing a whole thing called cold starts because they struggled with the model being able to generate the right formats from the beginning. So they actually ended up doing a sort of cold start prompt to get the model to generate things in the right way. So they ran a sort of supervised fine-tuning stage first before they started running their RL stage. Again, I have a whole video on that sort of cold start prompting. It's worth checking that out. But, for Deep Zero, they didn't do this. But, I think this little hack sort of just gets that into the right format. But as you can see there, from here to here, it is now generating the right outputs. And I could take that, I could literally copy and paste that out, and then I could run that into my verifiers, and then it would be able to come back and verify whether the output was correct. So this is exactly how they do this. Now, in this case, I am doing greedy. So basically, I am just getting the most probabilistic result from the model by default. But that's not actually how they do that within the paper. So if we look in the paper here for a second, you can see here is they actually tell you the parameters that they are using in the setup there. So you can see here, they're saying we set the maximum generation length to 32,768 tokens. Again, that's a little bit high for my machine. I sort of limited mine to 256, 512. They said, we found that using greedy decoding to evaluate long output results in higher repetition rates and significant variability. So they are defaulting to pass at K evaluation and report pass 1 using non-zero temperature. Specifically, we're using a sampling temperature of 0.6 and a top P value of 0.9 to generate K responses, typically between 4 and 64. Now, they're giving a lot of fancy words there, but essentially what this means is rather than taking the best probabilistic result and giving the model the ability to be as creative as it likes, is they're essentially going to set a couple of settings to control the outputs. Now, the first setting is the temperature. So temperature can be between 0 and 1. So 0 means it's not creative at all, and 1 means it can come up with any old nonsense it likes. 0.6 is sort of somewhere in between, so it's a little bit creative. It's going to come up with different ideas and different variations, but it's not going to be over the top wacky stuff, right? And the other one is this minus top P. So rather than looking at all of the possible results, all of the probable answers that the model could generate. Remember, this is a next token prediction model. So if you said the cat sat on the most probabilistic answer would be Matt, the least probabilistic answer would be something like cheese. The cat's not going to sit on the cheese. So the Matt would have a really high probability, but cheese would be much, much lower. However, if you're being super creative, and then there's a possibility that it could come back with the answer cheese. So what the sort of top P does is this at 0.95 is it's sort of getting rid of all of the outliers, and it's only going to look at the next tokens that are within the sort of top 95% percentile. So that's really what's happening. And again, I'm using temperature to control my creativity. And this is how you start to gain control. So in this case, when you do the sampling, then you're sort of lobbing off the most unlikely answers, and then you're trying to, with the temperature, sort of have a reasonable level of creativity, not having it being too wacky. So if I run this on my machine, I've got my inference CLI. I can pass in my sampler's top P. I can set my temperature to 0.6. And then top P is 0.95, and then I'm going to pass through that exact same prompt template that we had there, and then you can see it's going to come back with the sum of 10 is 20. To find the sum, you need to and then the answer there. This is exactly how this works. The only difference in this sense is I'm just returning one result at this stage. Now, if we remember in the paper, one of the things that they are saying there is they are going to typically do somewhere between 4 and 64 different samples. So now if I wanted to, one of the things I could do here is I could just add in another parameter, which is num responses. In this case, I'm going to set it to 4. By the way, I've just added in the think tag in there as well. And now when I run this, rather than generating one sample, you see it's going to come back with multiple samples. So it's going to come back here and say, what sample is 10? So there you go. You can see that it's came back, and then I've got 4 samples, sample 1 of 4. This chain of thought is first, remember it's within this think tag here. The first we need to understand the blah, 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 blah. And then the answer is 20. And then this one is 10 plus 10 equals 20. Answer is 20. So it's getting a much shorter chain of thought. And then here's another one to find the sum of 10, blah, 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 blah. And then the question asks for this, blah, blah, blah. And the answer is 20. So it's giving me 4 different answers. Now, remember it said somewhere between 4 and 64. So it could generate up 64 different generations of this. And that is what they're actually doing. They're just generating multiple responses here. And then they're going to just take the output here. So this, the question, blah, 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 within the answer, including the think tag there, and then it's going to run that to the verifier. And if the verifier says yes, this meets the format reward and the accuracy reward, you're going to get a score somewhere between 0 and 1, depending on whether it's met it or not. And that is literally how it works. That's actually what's happening underneath the hood. They are the exact same settings, and you can go and mess around with that on your machine and look at what the outputs are. But that is what is happening underneath the hood. Now, remember in my case, what I want to be able to do there is, rather than using the boxed answers, because then we're going to have to sort of teach the model how to get the boxed answers there, I want it to do return me a verifier answer. So I'm just going to pass in my template, which also includes verifier answer. So this prompt template is similar to the one that DeepSeek used, but rather than it just saying here is think and answer, then I'm asking it to come back with a verifier answer as well. And then I'm saying, hey, provide just the answer within verifier tags that can be checked by an automated process. And then if we do this here for a second, we run this on my machine. In this case, I'm going to return 1 response rather than 4. But what it will now do is generate out not just the think tag, but will also generate out the verifier tag as well. Okay, so now you can see it's came back. Again, this is why, again, in my other video, why we covered cold starts, why DeepSeek does this in this sense. You see here, it's generated the think tag, and then it's generated the answer, and it's came back with the verifier answer. But then it's also generated a whole bunch of nonsense after that as well. So again, this is something I can control by putting things like stop sequences in, or if I was to do a round of fine tune there, I could get the model to come back with these answers rather than having to reward it all the time and then eventually it comes back there. So this is why I still think, you know, fine tuning is an important part. But you can see, you know, just by making a little bit of a change here, it's going to come back with the right answer in the format that we want. So, and again, all of this is stuff that you can grab and then you can just run through the verifiers and then it can get its reward or it's not its reward. Now, the cool thing about math in general, and again, it's the same with things like code. If I want to, I can generate examples already. So if we take something like here, so what I am going to do here is I've got a little script in my Chuck Math. Again, in my cold start video, I go through the kind of Chuck Math project. But here in this case is a script called generate verifier samples, which will actually generate out a data set with the correct verifiers to use, the question, and what the gold answer is. So essentially it's all going to be good. So if I look in here for a second, and again, you can go and download this. In my data set here, I'm going to have a thing called prompt, solve the expression, blah, blah, blah. And then I'm going to say these are the verifiers that you can use. And the gold solution is the answer. So this script here will actually generate out you know, what the answer is for the various prompts. So again, to show you that working very, very quickly, if I go into the config here, maybe rather than generating 25 samples each, I'm just going to generate 1. You can see I've set my verifier URL. I'm going to set a difficulty, whether it's a hard math problem, an easy one, etc. And then what LLM is going to sort of convert the question into something sort of readable. So if I run that for a second, and now if I do Python generate verifier samples.py, it's going to read that config file, and then it's going to go off and generate all of the samples there. And as you see there, it's generating this out as you speak. Find the values of this arithmetic challenge, 8 minus 64. Tells you what the reward's going to be, what the verifiers are. So go use my URL. And again, you can set that to what you want. And then the gold solution answer is minus 56. And again, the LLM's not generating that. It's just doing sort of math compile and then working that out. If you want to put that to a file, then all you need to do is direct the output to a text file. So you see I'm doing that to the screen, but there's nothing stopping you. Just sort of say, output, and then say output sort of verifiers blah .jsonl, and then it's going to take that output and then put it out to a JSONL file. So that is how you could generate a data set. Again, I'm doing that for math, but again, you could do the same for limericks. You could do the same for code. Again, you're just going to set what verifier you're going to use. Notice there is no answer in this sense, so it doesn't have the chain of thought reasoning. So in my other video, I had a thing that generated the chain of thought reasoning through my math compiler, which is a better way of doing it. But in this case, I'm going to get the chain of thought reasoning from the LLM. So we don't need to do that. We just run it through the verifier and then we can get the chain of thought reasoning. And then finally, once that's actually done, one of the things I can then do is I can then go and generate out the responses. So in in a reinforcement learning world in GRPO, this would actually happen live, but I've created a little script here which will actually just read the generated data set that we have there with all the verifiers, and then we'll essentially run through that same script where it will generate the 4 sort of samples, etc. So you can see I've set a number of generations to 4. Again, you can set the device's MPS or CPU or CUDA, and then do in batch sizes. So if I just run this for a second, so if I just before I run that for a second, so you see here I've got this sort of math JSON-L, which is one I sort of generated earlier, where I've got sort of 75 math expressions there. I solve this, do that, tells you what the verifiers are, and then tells you what the gold solution is. And again, if I were to run this, for example, and then I'm just going to output my data set to output 3 there, 4 generations. I'm not going to fully run this because it's just going to take quite a long time. Remember, I'm running this against a very small model, whereas when DeepSeek did theirs, they're running against DeepSeek V3, which is a very large model in this sense, much larger than a 3 billion parameter Quen model. So you see there, that's the exact same template as you've had before, solve the expression, and then there's the assistant, generated think, blah, 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 exactly what you saw before. And then we're taking the output here, and then we're calling the verifier. So the first verifier that it's calling is the format verifier. You see strip match for think answer verifier answer. It gets a score of 0. And then you can see the next one here matches exactly. It generated the right answer. So 90 multiplied by 60. So the question in this case would have been 71 minus 90 multiplied by 60. You see the gold answer is minus 5329. The model's generated that answer, and it's got a score of 1. So that is exactly what happens when DeepSeek is sort of training their model. Again, I'm using verifier rather than box, but it's pretty much the same. The only difference that they are doing is they're using reinforcement learning with the GRPO technique. Again, I will cover that in another video. What I'm doing in this case is I am just going to grab the outputs here, and then I'm going to store them in a file, and then we can use that for fine-tuning later on. So I'm going to kill this for a second. We're just going to clear this. And then at the end of that run, you are effectively going to get an output that looks like this, item long prompt. You see the original prompt that you got there. Then you get the short prompt, solve the expression 71 minus 90 minus 60. And then you see the verifiers associated, and then the gold solution. And then the last thing that you're going to get here is the responses. So you see the output think, perform this, answer, verify, answer, think, blah, blah, blah. So you get the 4 different responses that you generated, or however many you responded. And then you get the logits, so the probabilities for each response, whether it was a good answer, a bad answer, etc. And that can help the model when you're doing reinforcement learning. What the rewards are, so this was 1, 1, 1, 1, so it got it all correct. And then any of the feedback. Again, feedback's not used, it's just the kind of score there. So now that we've got that in that format, one of the things that you can do in this case, so in my case, I can actually just run a fine tune of this. So if I just take the output that we generated here, put it to this output, this is just going to do a supervised fine tune of that file that we saw there, run it in this case for something like 5 epochs. It will generate this, and then that's going to generate the underlying model. So once that model is generated, so you can see here in my output folder, here is the kind of math student 2 model, which is the output of that file that we sort of just ran there. And then if I just pass in here, so I'm going to pass in my model path into this script called Python infer student, which is just allows you to run against the model that you just generated. I'm going to pass in output math student 2, and then I'm going to run this calculation here. And you're going to see it's going to do a terrible result because it's really just a very small set of data that I've sort of put in here. So it's definitely not been tuned for long enough. I've not generated enough data there. But what you will see from this is, although that it will get the answer wrong, it has picked up the the think and verifier answer kind of reasoning here. So you can see here, model output, think, first subtract 16 from it, which is 16, add to 12, which gives you the result, and the think answer, 16 plus 12 is equal to 18, and then verify answer is 18. So again, it's got the answer wrong in this sense, but you can see it has picked up the think and the answer. And again, if I generate more data, or if we were doing reinforcement learning, if we were doing GRPO, which we'll do in a future video, then you will see that it would start to get this right. Also, remember, this has been trained from a 3 billion parameter model. So the chain of thought outputs, although it was getting it right, are not great chain of thoughts, right? So if I come back into this for a second, and we actually look at the data set that was actually generated there. So if we look at math output here, it's not great. First perform the multiplication operation, then subtract the product, and then this is the answer. So it's not the best chain of thoughts in the world. And again, if I used a better model, if I used a bigger model, maybe a 7 billion parameter model, or in DeepSeek's cases, 600 odd billion parameter model, with 32 billion parameters active at any point, it's going to generate really good chains of thought. But in this case, it's not going to be so great. That is kind of why, if I then compare this to, remember in my other video where I generate out the chains of thoughts using my math compiler. So these are really good chains of thought, as you can kind of see there. And then I cold start with them, and then I fine tune off of that. Again, even though it's a very small data set, it's 120 prompts, because the chain of thoughts there are so good, if I were to run that exact same script here, so in this case, I'm going to run in first student again, but this time I'm going to use my SFT output, which is that data set that I just showed you a second. I'm going to give it the same question, which is calculate 32 minus 16 plus 12. Again, it's got all the thinking, the reasoning, but because I've generated that from data that comes from my synthetic math compiler, and the chains of thought are so good, much better than the chains of thought that's coming from Qwen there, you can see it's coming back with the right answer, which is 28. But you can see the difference in the reasoning, right? Think, problem, calculate 32 minus 16 plus 12, reasoning, begin with the given expression, according to the order, PEMDAS, first subtract 16 from 32, next add 12 to the result, and thus the final answer is 28, and then comes back there. And again, you can see how I did this in my other video, the cold start video, but go check that out, and then you'll see how I use synthetic data to be able to generate. But the quality of those chains of thought are much better than the chains of thought that I'm getting from the Qwen model. Now, don't get me wrong, if I run lots and lots and lots of chains of thoughts and then come back and forward, use reinforcement learning, it's eventually going to get to really good outputs, but it's just going to take a long time to do that. So again, I think when you start to move into, and again, I'm showing you math, but you can do this with code, you can do this with limericks, haikus, whatever. So the nice thing about this technique over my cold start technique is with this technique, using the verifiers purely, you don't need to know the answers in advance, right? The model will give you an answer, a chain of thought that worked, and then you're going to train off of that chain of thought. Whereas with my cold start technique, I'm using my synthetic data generation to get to much higher quality results. Again, with better models, better chains of thoughts, etc., more training time, I would probably get just as good a chain of thoughts as I got from my synthetic data, which sort of jump starts. Again, you could use the same techniques for things like code, etc. I mean, again, I have provided you, if you wanted to do a fine tune, maybe I'll cover this on another video, but I do have in that Chuck fine tune on my GitHub, a fine-tuned trainer called SFT Train CLI. Again, I'll probably update these over time. You can put in my cold start data completions. You can then generate that model, output it in math SFT2. Again, it's 120 prompts, but again, it does a fabulous job just off the back of that as well. And then it will take you a few minutes to run on your machine, and then it's going to generate high quality. So I think this sort of cold start together with reinforcement learning combined with the verifiers is going to be really important. I'm not going to cover reinforcement learning on this video just because I think that deserves a lot longer on how to do that properly. So probably my next video, I'm going to cover reinforcement learning with GRPO, but the method of generating the prompts, the way of doing sampling is exactly what we're going to use within GRPO, and the method of being able to use verifiers. So everything I showed you with verifiers today is what we would use with GRPO as well. So the only difference is I use fine tuning at the end rather than using reinforcement learning, but I'll cover that in the next video. But I hope you realize the concept of cold starting. Again, check out the video on that. The concept of sampling and generating outputs from the model, and then combining that with verifiers to get your reward is really, really powerful. And then I hope you're going to go off and create a whole ton of verifiers. And again, maybe in a future video, we're going to explore how we can then, rather than just deal with the score, how we can push the feedback back into the model so that we can evoke even better chains of thoughts. Because I think that's the missing link there from what DeepSeek did, is being able to take the feedback from the verifier, feed that back in, and then be able to sort of run another round and get even better chains of thought. So we'll probably cover that in another video. And then maybe in another video, we'll probably explore looking at processes as well, and whether we can clean up the chains of thought so it generates the rules, and then we can do process modeling, etc. So anyway, I hope you found this video useful, and hopefully it gives you a bit better understanding of kind of reward modeling and verifiers, and hopefully you'll go off and create some fun stuff. Anyway, I will catch you on the next video.